Section 9-3, linear momentum, which we got to see a little bit in lab just before the break. So linear momentum, as we discussed, is defined as P, we use a P for linear momentum, is equal to mass times velocity. Now note, this is a vector equation, right? There are the arrows above it, and that shows that direction here does matter. Unlike with energy, where we're like, direction, whatever, it's just speed. Here, this is velocity again, and our momentum is pointing in the same direction as the velocity. Mass is always going to be positive, so the momentum will always have the exact same direction as the velocity. And the units of it, as we saw in lab, or as you hopefully saw in lab, are just that of mass times velocity. So kilograms times meters per second. We don't have a fancy unit for linear momentum, and that's okay. So if you just remember mass times velocity, you have your momentum. So that's a good one to store up there in your brain. Now, the interesting thing with momentum is it can only be changed by a net external force. If you have a net external force, that will change your momentum. And so you could then say that the time rate of change of momentum of a particle is equal to the net force acting on the particle, and it will be in the same direction as that net force, right? If I have my marker, if I apply a net force on it, then the change in momentum will be in the same direction as that net force that I applied. So a way to write that very wordy sentence mathematically is you can say that the net force, F net, is equal to the derivative with respect to time of the momentum. So the rate of change of momentum with respect to time, where this is still a vector equation and the directions here do matter. We could also sum the momenta for several particles to find the linear momentum of the system of particles. Since it's the system, we use a capital P. We saw that a little bit in lab, where when we considered the momentum of both balls at once, then we used a capital P, and that's equal to the total mass m times the velocity of the center of mass. Okay. And similarly, we could also write Newton's second law for a system of particles, and the only thing that changes from the previous version of writing it is we now have a capital P as opposed to a lowercase p, because it's now a system of particles instead of just a single particle. But still, as if there's a net force acting on the system, then it can change the linear momentum of the system. And if there is no net force acting on the system, then the total linear momentum of a system of particles cannot change. And that's what we examined in lab last week, is we set up a system of particles and they had some initial momentum, right? Maybe they were both moving, maybe one of them was moving, whatever you had it, but there was no net external force. And so we saw that the total linear momentum of the system was constant throughout. Right, let's try a checkpoint. So the figure here gives the magnitude P of the linear momentum versus time for a particle moving along an axis. A force directed along the axis acts on the particle. Rank the 4 regions according to the magnitude of the force greatest first. There's 4 answers. Then there's also a question, in which region is the particle slowing? So I want you to think about this on your own before you continue the video. So go ahead and pause it now. Okay, hopefully you paused. Now we can take a peek at the answer. So it is C in terms of the magnitude of the force, right? Where region 1 is the greatest amount of force because it's the steepest in terms of slope. We know that force is equal to the change in momentum with respect to time, dp dt. So if you have a larger slope, then you also have a larger change in momentum over that time interval, right? 3 has an overall larger change in momentum, but it's also over a longer time interval. So it's not a greater force, it's just a force acting over a longer time. And notice, because it's describing the magnitude of the force, 3 is still greater than 2 and 4. It's a negative slope, but the amount of force in 3, the slope, is still more than 2 and 4, which have a slope of 0, because there's no change in momentum, right? The momentum for 2 is staying at that constant non-zero value. Momentum of 4 is staying at that steady value of 0. So those have the least amount of force, and then where the particle is slowing is in region 3. And there's a couple ways to look at this, right? One is that it's a negative slope, and so it's losing momentum. The amount of momentum is going down, which you could also tie to, hey, momentum is mass times velocity. So if we have some amount of velocity up here, and we go down to 0 velocity, that means we are losing speed. So the particle is indeed slowing down in region 3. Regions 2 and 4, 2, it's traveling at a constant velocity, so not slowing, and 4, it's just stationary, so also not slowing. It's completely slowed. All right, so that is linear momentum, and that sets us up to be able to later apply it to what we've seen in lab, the conservation of momentum. That's coming, but we'll take a little bit more to get there first. See you soon.